Section 17.4 talks about conjugate addition. Generally speaking, professors would choose HCl or HBr and ask you to predict the products of a diene reacting with those at either low temperature or high temperature. Before we jump too far into this, let's review what we know about carbocation stability. Now, for your carbocation stability, remember that first of all, if you can have a resonance stabilized carbocation, that is good. Aside from that, we know that tertiary carbocations are more stable than secondary, and we don't ever form primary carbocations in a curved arrow reaction mechanism. The second thing we want to talk about is the Markovnikov addition, okay, which is something that we just memorized, wrote memorization, but it's based off of the carbocation stability and the mechanism. Okay, so Markovnikov addition of alkenes. All right, and I want to talk about this in a greater detail. So if we have an alkene like this, and we add HCl, we get that. We don't get the other regioisomer. That is to say, we don't get 1-chlorobutane. Okay? Okay. Unfortunately, a lot of students just memorize that. Okay, I got to remember this, but not that. But let's talk about the mechanism of this reaction right here and why you don't form that reaction. Okay? So when this alkene reacts with hydrogen chloride, okay, there's two arrows there to show the protonation, okay? And the proton ends up going on the rightmost carbon. We don't draw hydrogens in the organic chemistry class, so it's kind of looks like it disappeared, but actually we've added it, okay? So I'm going to put the H there, and you'll see that this is a secondary carbocation now, which is generally accepted, okay, that we can draw that. And after chloride engages, because it's negative, engages that positively charged carbon, it forms the product, okay? Now, what does not happen is protonation the other way to give you an H being added to that secondary carbon and then a primary carbocation, right? Because primary carbocations cannot be formed. Sure, we could draw it on paper. It looks all good here, but that's not going to happen, okay? Primary carbocations are very highly unstable and don't show up except in astronomy and gas phase experiments and stuff, okay? So that's why this is not formed. It goes back to carbocation stability. A way to just condense all that into a simple rule is the rich get richer. Markovnikov addition of alkenes occurs such that the carbon with more hydrogens gets the hydrogen, and the other carbon gets the whatever, the chlorine or bromine in this case, okay? So let's talk about conjugate addition of alkenes, of dienes, okay? So when I add HCl to this, you can get two potential products, okay? I'm going to number this carbon chain just from right to left, and the chlorine here can add to carbon 2, and the hydrogen could add to carbon 1. That's what we call the 1,2 addition. Okay, so because the hydrogen has added to carbon 1 and the chlorine has added to carbon 2, we call this the 1,2 addition product. Okay. And dienes, and that's going to be favored at low temperature. Okay. What's low temperature? 0 degrees Celsius, minus 20 degrees Celsius, minus 40 degrees Celsius, something like that, okay? We have different solvents that don't freeze at very low temperatures, and we use those with different dry ice or refrigeration processes and techniques, okay? So don't worry too much about the temperature there. We can also add HCl And here's where things get really weird for some students, and they don't quite see the pattern until we draw the mechanism, and then it all clicks together for students. Okay, so here I have my 4 carbons all labeled out, and I have all those carbons numbered here in the product. And now what I'm going to draw is a hydrogen, okay, attaching to carbon 1, and a chlorine attaching to carbon 4. So that looks okay, but then you'll notice that the double bond is now in a completely different region in the molecule. Okay, now we have a double bond between carbons 2 and 3, so that looks very weird, very new. Okay, this is what we call the 1,4 addition product. Okay, and that occurs at high temperature. Okay, what's high temperature? Room temperature, boiling, whatever, something like that, okay? Now, the way I memorized this when I was a student is that 1, 2 are lower numbers, so I remembered that was lower temperature or associated with low temperature. And 1, 4, 4 is a higher number, right? So I associated that with a higher temperature. So if that helps you out, great, but you still need to remember which carbons and how to draw these molecules, okay? So let me take you through the mechanism here for the 1,2 addition. Okay, so once again, we'll just use butadiene here as our typical reactant, and we're going to add HCl to this. Okay, and let's go ahead and draw what we get. Okay, so this alkene is going to attack the HCl, and you're going to form, I'll draw the H here so we can see where it's been added. We're going to form not just a secondary carbocation, but a carbocation that's resonance stabilized, okay? And we call this an allylic carbocation. An allylic carbocation is a carbocation that's conjugated. The carbocation is an empty p orbital, and it's right next to the p orbitals of a pi bond. So those 3 p orbitals are all in a line or aligned or in a row, and so we call that conjugated, okay? So that's an allylic carbocation. Now here we don't need to do much with resonance. We just take the chloride and we attack that carbon 2, and we're done with the reaction. And I'll draw the product once again. This time I'm going to leave off the hydrogen on carbon 1, and if you're confused by that or need to see it when you're taking notes while you're watching this video, add in the H if you need to, okay? This is the 1,2 addition. All these reactions are in equilibrium, so we do it at low temperature to trap out that kinetic product. Section 5 in the textbook goes into a lot of explanation about why this forms at low temperature. Okay, I'm not going to explain that here in this video. Now, what about the mechanism for the 1,4 addition product? Okay, now the reaction, once again, starts out extremely similar. Okay, you have HCl, and you have this diene, okay? And yeah, you form this nice resonance stabilized secondary carbocation, okay? But here is the trick. You want to use resonance at this stage. And once again, all these steps are going to be in equilibrium, and this is at high temperature, okay? High temperature. So let's go ahead and show the resonance structure, okay? So we take the pi bonds, the pi bonding electrons, and we scoot them over towards the carbocation. When you do this, the new resonance structure is going to look like this, okay? Now, I know what you're thinking. You're thinking, well, we can't do that. That's a primary carbocation. You just said those are really unstable. They don't form. But remember, resonance is kind of a lie we tell ourselves. It's one representation of the real structure that we really can't visualize, okay? So these two structures right here are averaged together to give you the resonance hybrid, which we don't really know what it looks like, okay? But we can draw Lewis structures for individual contributors, okay? Now, if we number the carbon atoms here on the starting structure, we can see how I've added the hydrogen to carbon 1. And what I need to do is attach a chloride or a chlorine atom to carbon 4. And I can do that in another step if I take chloride, okay, and attack that partial positive charge on the primary carbon on the left. And that will give me, okay, again, all of these steps are in equilibrium. That's going to give me the 1,4 addition product. So in this molecule, we have the hydrogen added to carbon 1 and the chlorine added to carbon 4. So that's why we call it the 1,4 addition product, and that happens at high temperature. Okay, so let me show you some examples. Here's a molecule that we would name it 1,3 cyclohexadiene. Okay, and let's predict and draw the products that would occur if we reacted this with HBr at low temperature and HBr at high temperature. Okay, so at low temperature, we want to just take one of the alkenes. It's very symmetrical here. So I'll take carbons 1 and 2. I'll leave the alkene alone at carbons 3 and 4. Okay, so it's going to be an alkene there at carbons 3 and 4. And carbon 1, remember, we're going to add the H. And carbon 2, we're going to add the bromine. We're always going to form an allylic product. Okay, this is an allylic halide. That is to say that this carbon right here is next to the pi bond. In the 1,4 addition, what do we need to do? We need to attach a hydrogen to carbon 1. We need to attach the halogen at carbon 4. And the double bond, where is that going to be? That double bond is going to be between carbons 2 and 3. So that's the pattern here. And if you look, you can see that we again have an allylic halide. The bromine is bonded to a carbon that's next to the pi bond. Okay. Let's do a practice problem from the textbook now. Problem 17.7. Problem 17.7 is a great review problem. As you can see, the reagents are very simple: HCl and HBr. There's no reason to memorize a whole bunch of other reagents that do indeed react with dienes. Now, all of these are conjugated, so you don't have to think too much about that, okay? Now, when you have a very symmetrical alkene, there's not going to be a choice as to which way you number 1, 2, 3, 4 or 4, 3, 2, 1. For example, in problem E here, it's a plane of symmetry down the center of the molecule. So this is going to be very simple, okay? Now, you can just number it from, in a clockwise way, which is normally how I number rings. So for example, for part E, we would once again, for the 1,2 addition product, we would add hydrogen to carbon 1, and we would add a bromine to carbon 2, okay? And the double bond between carbons 3 and 4 remains the same. And the 1,4 addition product, okay, we add hydrogen to carbon 1, and we add bromine to carbon 4, and the double bond moves to be between carbons 2 and 3, okay? So when you have a very symmetrical molecule where the two sides, two ends, are essentially equivalent, you don't have to do a whole lot of thinking, okay? But look at problem D here. Okay. Problem D does not have a plane of symmetry. Do we number 1, 2, 3, 4 clockwise or 1, 2, 3, 4 counterclockwise? Okay, and this is going to require some more thought. So I want to work on problem D here on the next page. Make sure I copy it correctly. It's with hydrogen bromide, okay? And you have to realize that you can number it two different ways. You could number it this way, and you could draw two different products, or now, when I say numbering it two different ways, I don't mean for accurate naming purposes. I just mean for reaction, okay? So remember, a 1,2 addition, you're going to add the H and the Br about carbon 1 and 2, but here, obviously, it's going to be a different molecule because you have the methyl on the other side, whereas carbons 1 and 2, you have the methyl on that side, okay? So here, it might be helpful to think about the mechanism. When the 1,2 addition occurs, what is transpiring? We have protonation at carbon 1. We have a carbocation at carbon 2. Bromide comes in, attacks the carbocation, and gives you the 1,2 addition product. Now let's look at the alternative. If I numbered the ring in a counterclockwise fashion, 1, 2, 3, 4, like down on the bottom, what's going to happen? Okay, carbon 1 is going to protonate by reaction with HBr. Bromide is going to attack that carbocation. Giving me the 1,2 addition product. Now, you can't just look at the starting structures and just imagine all of this in your head. It takes quite a bit of doodling to figure this out. Now that we have everything on the screen here, we can analyze these two and compare and contrast them, okay? Each of them require a protonation. Each of them require production of an allylic carbocation. Now, this carbocation is allylic, which means it's adjacent to the pi bond, but it's tertiary. Tertiary means more stable, okay? Means lower activation energy. It means that this is going to form. On the bottom route, we have an allylic carbocation. That is to say, it's adjacent to the pi bond, but it's secondary, okay? Secondary carbocations are less stable than tertiary, okay? So the major product would be the 1,2 addition product on the top right. Now, I haven't looked at the solution manual for this textbook. Maybe they want you to draw both of the 1,2 addition products that you would get and both of the 1,4 addition products that you get, okay? But when you have to make a choice about which 1,2 addition product is better, look at the mechanism to decide, okay? I know it's not an answer students like to hear. Isn't there just something I could memorize, like Markovnikov's rule or something? I haven't found a rule that could really be succinctly stated that would help my students. So you have to look at the mechanism, okay? I haven't even gone into the 1,4 addition product, but let's go ahead and do that, okay? So let's down below number these rings in the two potential ways, okay? Now I know what the 1,4 addition product is going to look like. I can just draw that. Let's see if there's any difference at all. So when this reacts with HBr, carbon 1 is going to have the hydrogen here. The bromine is going to be at carbon 4. Okay? It's going to look like that. And when this reacts with HBr, carbon 1 is going to be the hydrogen. Carbon 4 is going to be the halogen. Okay? And those two molecules are definitely different. Okay? The molecule on top has the bromine and methyl groups on opposite sides of the ring. And in the molecule on the bottom, the bromine and methyl are on the same side of the ring. So let's look at the mechanisms and maybe see if there's a difference. If there's no difference, then we can't say, oh, this is going to form, that's not. Okay? So both of these are 1,4 addition products. Which is right? Are they both right? Is one right? So let's go to the next page and work through the mechanism. So I'll number these again so we can keep track very carefully about what might be transpiring. And we're treating these with HBr, okay? So we always protonate carbon 1. Okay. We have this nice tertiary allylic carbocation. Okay. I'll draw the H in here in a different color just to really emphasize it this time. And now what we want to do is draw the resonance structure. Okay, so remember with the 1,4 mechanism, you have to draw the resonance structure. And that's to position the positive charge way over by carbon 4. Okay? And then bromide, which is the counter ion, is floating around. That's going to attack, and that's going to end up at carbon 4. So you'll notice my use of arrows. Sometimes they're reaction arrows, sometimes they're resonance arrows. Okay? So that's the 1,4 product. Now let's look at the other numbering system to see what might be happening. So again, I'm going to attack HBr. Whoops, I made a mistake, didn't I? We always protonate carbon 1. Remember how I was saying that before? So here's my proton attached that's been added. Okay, so there's my positive charge. So there we go. That's secondary allylic. Okay, secondary allylic. Okay. And now if I draw a resonance structure, okay, you will see how it's also secondary and allylic. And bromide comes in, attacks, gives me the other possible 1,4 addition product. Okay. So the difference between this 1,4 and this 1,4 addition product are the hydrogen and bromine are just swapped, okay? When you analyze and figure out which one of these reactions might be better, you want to pick the more substituted carbocation, and that's going to tell you which product is going to be most stable, okay? So the two products that we would expect from part D would be the 1,2 and 1,4 addition reaction products with that numbering system, okay? Here's the 1,2 product, and over here is the 1,4 product, okay? There's no really easy way to do that. When you have a symmetrical alkene or diene, there's only one choice, okay? So if you have a problem like E or F or C, that should be very easy, and you should know carbons 1 and 2 or carbons 1 and 4, done deal. But if you have something that's unsymmetrical, that most likely would be a homework question that you would encounter. You need to draw the mechanisms and figure out which one of the carbocations is most stable and which one are you most likely going to proceed through to give you the reaction products, okay? So that's it for conjugate addition that I want to talk about, okay? You might want to read section 17.5 to understand the kinetics and thermodynamics and equilibrium a little bit more on your own.